Hello everyone. Today's lesson is discussing the normal or the Gaussian distribution. The importance of this distribution as part of the continuous distributions and the reason why we study it separately from the other two continuous distributions that we have looked at so far, which were the uniform and the exponential distribution. Now the normal, and sometimes it's called also Gaussian distribution, is a distribution that is most widely used in natural representation of random phenomena. And the reason for that is that there is a theorem called the central limit theorem, right, which was discovered in 1733 by Gauss a little bit later, and in 1733 by De Moivre, which states that if you have several sources of randomnesses added together, then regardless of how each one of them, so one of them could be normal, one of them could be exponential, the other could be with randomness that does not follow a particular distribution, and so on. If you add all of them together to produce some value, so this value has lots of random sources added together, then this resulting random variable of the sum of too many random variables is going to be the result. The resulting random variable is going to be following the bell-shaped curve, the Gaussian curve, or what we call the normal distribution. And this is regardless of what were the distributions of each individual random variable. Now that's a very nice result, because again, if you look at most of natural randomized phenomena, they come actually from multiple sources of randomnesses added together, and the best example was the example of the temperature in the room that I gave earlier during your previous lectures. So that's why the normal distribution is an important one. Most of natural physical random phenomena that happens in the lab, happens because of noise, happens because of measurement errors, all these eventually they follow a normal distribution with certain parameters. Now if we look at the normal distribution, the small f of x for that distribution follows the function that we see here, where x is the random variable. So the probability density function follows the expression that we see here. There are two parameters to this in addition to the random variable itself, right? And the two parameters are the standard deviation, and sigma square is going to be the variance, and mu is the mean of the normal distribution. So if you are given a particular normal distribution, small f of x, if you know the small f of x, then immediately you can deduce by comparison with this formula, you can deduce what's the mean and what's the standard deviation or the variance of that, right? Directly from the expression. Now, since this expression is quite complicated, in many cases, the normal distribution is represented by n, right? And then in the first part, we have the mean. In the second part, we have the variance. So for example, a normal distribution with mean equal to 1 and a variance equal to 4 is going to be represented as n with 1 and 4, right? Which means that it has this expression where this is substituted by 1, and sigma square is 4, so sigma is 2, right? Okay. And that is being mentioned clearly here. Now, the variance of the normal distribution controls the width. So the bigger the variance, the bigger the width of the distribution, while the mean value determines the center of the bell-shaped curve. Notice that the curve is symmetric around its mean. So the left side is exactly symmetric to the right side. And that symmetry is quite useful in calculating probabilities later on. Okay. Another nice thing of the normal distribution is that if around the mean value you take a width equal to 3 sigma from both sides, so mu plus 3 sigma, mu minus 3 sigma, then the total area under the curve, which is the probability that your random variable x is greater than this value, less than this value. So the probability that your random variable is somewhere here, that the value of your random variable is somewhere here, is 0.997, which means that most of the time your random variable that follows a normal distribution will have a value most of the time. Notice 0.997, a very high probability, right? Most of the time it will have a value greater than the mean minus 3 sigma, less than the mean plus 3 sigma. This is useful sometimes in approximating the calculations. Now notice that in order to calculate the probability that x is greater than some value a less than some value b, you have to integrate the exponential, that's the expression of the normal distribution, the exponential of minus x minus mu squared dx. Now this integral cannot be solved in closed formula. You cannot really find a symbolic solution for this integral. Of course you integrate from a to b, right? So the only way is to calculate this integral using numeric calculations. So that's why in order to calculate the probabilities for normal distributions, we actually use tables. And the coming few slides will show us how do we use those tables. Okay. There is one particular important normal distribution among the existing normal distributions, which is called the standardized or the standard normal distribution. Now that's again a normal distribution with the particular property that its mean is equal to 0 and its variance is equal to 1. And if we use x to represent the general random variable, including the one that follows any normal distribution with any mean and any variance, then for the standard normal distribution, we typically use the letter z. So whenever you see z capital or z small dealing with normal distributions, this means that you are dealing with a standard normal distribution. Whenever you see x capital or x small dealing with normal distributions, then this typically means that you are dealing with a generalized normal distribution with any value for the mean and any value for the variance. If the mean is not equal to 0 and the variance is not equal to 1, then my normal distribution is not a standard one. Now, why do we need to worry more about the standard normal distribution? Because as I mentioned, the calculation of the integral, right, in order to calculate probabilities under the small f of x, the area under the small f of x to calculate probabilities in the normal distribution case, has an integral of e to the minus x squared, which cannot be solved except numerically, but we cannot solve it for every single possible value of the mean and the variance. Notice that the mean and the variance can take any real value, right? So now we need to solve these integrals for all possible values of mu and all possible values of sigma squared. That's very difficult. So the solution was to solve this numeric integral for the case of the standard normal distribution. So for the mean equals 0 and for the variance equal 1. And by the way, in that case, we call the cumulative distribution the probability that my standard normal distribution is less than a particular z. This is the capital F of z, right? We call that phi of z, right? Just naming. So whenever you see phi of z, it simply means that you are looking for the capital F of the standard normal distribution, which is equal to the probability that a standard normal distribution is less than or equal to a particular value. So whenever you see, for example, phi of 3, this means that you are looking for the probability that z is less than 3, right? And so on, right? Which is also the capital F of 3 for the standard normal distribution. Anyways, so as I mentioned, that integral for the standard normal distribution is solved for normal distributions with mean equal to 0 with variance equal to 1 and put into tables. And not any integral. We are solving, or they have solved, the phi of z for all possible values of z. Of course, discrete values. Have to pick some values with some precision, right? And then put that into a table. And the table has a particular organization. So if we look at that table, we see it right here, okay? The calculation is 5z, which is represented by the area that you see here. So the probability that your random variable is smaller than a particular given z, right? So it goes from z all the way to minus infinity. Probability that capital Z is less than or equal to a certain value, right? And then it's given in a table format as we see right here, where z, so this value, this start point of calculating the area, right, is given by the values here, but not only the values here. The values here shows the first two digits, so the one before the decimal and the one after the decimal, right? And then as you go across the different columns, the value of z is increased in the second digit. So for example, if I'm looking at this cell, this will give me the phi of z, where z is equal to 0.6 plus 0.01, which means z is equal to 0.61, right? So again, the example that I mentioned right now, if I take this particular value, then this value is equal to phi of z. What's the value of z? It's 0.6 plus 0.01, which is 0.61, which is the probability that my standard normal distribution, by definition, is less than 0.61. This is phi of z, and this is the probability that z is less, z capital is less than a particular, where the z here is 0.61, right? So I can simply say that this probability is equal directly to the value that I get from here. And what's that value? It's 0.729069, right? The value that you see directly here, okay? So another example, find, for example, the probability that z is less than 3.22, for example, okay? So this is equal to phi of 3.22, just a definition. This probability, this cumulative probability value is equal to this. How do I get this from the table? I'll go to 3.2, right? And then move until I get to 22, right? Then the value of this probability that I'm looking for is equal to what you get from there. So it's 0.9999359, right? Directly from the table, and so on, right? So this is how you use this table to get probabilities. You can use the table in two ways. Either to get the probability for a particular z, or given a particular probability, for example, what's the z that corresponds to a probability of 0.99609, then you look it up, 6093, so you look up this value in the table until you find it, and then you get the corresponding value. The z value in this case is 2.66, right? So you can use this table both ways. Either you are given a z and you find the probability, or you are given the probability and you find the corresponding z. Now, what if the probability is different? What if, for example, I'm looking for the probability that z is greater than a value? Because that table shows me only, remember, the table shows the probability that z is less than a particular value, right? So what if I want to get a probability that z is greater? As we know before, this is simply 1 minus the probability that z is smaller, and then we get this from the table, substituted in this formula, you get the probability. What if z is greater than a certain value, less than the other? Then you are looking for the probability that z is less than this, minus the probability that it is less than this. We have discussed these mappings before, and the areas here shows you why these mappings are correct, by looking at the areas and the subtraction of the areas under the curve and the addition of the area under the curve and so on, right? Now, you notice here that you have a negative value. The table that we saw in the previous slide does not have a negative value. There is actually another table for the negative values. So typically in exams or when you are solving problems or whatever, you have the two tables for the positive and the negative value. Let me bring the table to also mention something which is very important. So placeholder, and for an existing image, let's make this placeholder large enough so we can see exactly what's going to be there. Let's pick a picture, and the picture is for the table, right? And then let's look at this. So remember that if you notice the values here, they end at 3.99. Okay, what if I'm looking for the probability that x is less than 6, for example? Sorry, z, right? We are still in this whole table dealing with the standardized normal distribution. So in that case, how can I get it from the table if the table stops at 3.99? Well, if you notice, the probabilities have been increasing, and then when you reach this value, the 3.99, you are almost reaching 1. So anything greater than this is going to be approximately with a probability equal to 1. You can safely approximate that to a probability equal to 1, right? And also, what if I get some in-between values? So 1.7, for example, 1.732, that's the value. So the probability that z is less than this. So again, just you can truncate or approximate. So 1.73 is going to be here, right? And then that's it. Use this value as an approximation. Okay, so these are just important tips when you are dealing with the situation here. Okay, so here's an example. Find the value of z. Now this is a bit of like a complicated example. Find the value of small z such that the probability of your standard normal distribution, capital Z, is greater than this unknown value with negative and less than the same unknown value with positive is equal to 0.99. So simply here, this can be mapped into the probability that Z is less than small z minus the probability that z is less than the minus small z, right? Again, if we have a range greater than a value, less than a value, we can map it to this, right? Now notice that from the symmetry, we can see that the probability of being smaller than this z, any z, right, is the area coming from here going all the way back, right? And the probability of being smaller than the minus of that z is coming from here going all the way back. Now this one coming from here going all the way back will have the area in this part, right? Which is exactly equivalent to the area in this part because of the symmetry, right? So if this is the z and this is the minus z, right, then this area must be equal to this area, right? Starting from here going all the way, starting from here going all the way. Now what's this? This part is the probability that z is greater than the positive value, unknown value z, right? Which is equal to 1 minus the probability that this z is less than the positive value z, right? So now this, which is this, is equal to this part, is equal to this part. And the other part is this one. So if I append those together, I will end up with the probability that minus z less than this less than z is equal to the probability that z is less than small z unknown minus, and then you put that other part, right? 1 minus the probability that z is less than the small z, right? And then you close this. So if you aggregate these, you will end up with there is a minus outside, right? So this becomes minus, this becomes positive. So you end up with 2p of z less than unknown value z minus 1. And this is equal to the 0.99 given here, right? So simply, if you are looking for this probability, right? If you substitute, you get probability of z less than the unknown value z, right, is equal to, take the 1 to the other side, right? So 1.99 and then divide by the 2 divided by 2, which is equal to 1.99 divided by 2 is equal to 0.995, right? So now the problem has scaled down to find the z, the unknown z, that corresponds to 0.995 probability. So again, this problem can be solved, as we said before, by using the table in the inverse manner. So simply just let's add like the table here so we can see the problem. Just make it a bit larger so we can actually see what we need to see. Let's go get the table and try to find, remember, we are looking for 0.995, right? So let's move on the table. 0.99, so 0.993, 0.994, 0.995. Wow, I can find it, right? So this corresponds, this probability corresponds to what z value? It corresponds to 2.58. So simply we can go here and say that our small z from the table is equal to 2 point, remember, 0.995, right? So 2.58. And then voila, I found the required z, right? And that's the solution that you see right here, okay? So we have learned a few things here, how to play this trick of mapping, how to use the symmetry, right, of the curve to solve similar problems, and also how to use the table in the inverse manner. So given the probability, you find the corresponding z value, right? So how is this useful in the case that we have to deal with a generalized normal distribution, so a normal distribution that does not follow the standard? So far we have been using the table to get the value of the probability cumulative distribution function, the capital phi, or the probability that my normal standard distribution is less than a particular value, right, from the table. Now what if my distribution is a generalized distribution x where it has a mu that's not equal to 0 or a variance that's not equal to 1, or both? So the mu is not equal to 0 and the variance is not equal to 1, right? In that case, how can I deal with the problem? There is a mapping that allows you to move from the non-standard to the standard normal distribution. So if you have such a distribution that has a certain mean and a certain variance, you can map it to a standard normal distribution by taking x, subtract the mean, and then divide by the standard deviation. So not sigma square, by sigma only, right? If you do this, then what you will get is a standard normal distribution. So this will correspond to a mean equal to 0 and a variance equal to 1 if you do this operation. Now, what does this mean? Right? Let's see if we have to solve a problem. Suppose that the current measurement in a wire assumed to follow a normal distribution with a mean equal to 10 milliamperes. So now the mean is not equal to 0, and a variance of 4 milliamperes squared. So the variance also is not equal to 1, right? What's the probability that the measurement of the current will exceed 13 milliampere? So what's required here is the probability that my current is greater than 13, which we know is equal to 1 minus the probability that the current is less than 13. Nice. But I cannot use this in the table because this x does not have a mean equal to 0, does not have a variance equal to 1, right? Because we know that the mean and the variance of this random distribution x is not, it follows a normal distribution, but it's not standardized. So what should I do? In order to get this probability, I'm going to say that it is equivalent to the probability that x minus mu divided by sigma is less than, let's do the same. So here we write it in symbols, here we write it in values, right? 13 minus mu minus 10 divided by sigma, the square root of this, over 2, right? So this probability is exactly the same as this. Now we know that this, from the previous slide, this is actually z. It's a standard normal distribution, right? So finding this probability for a non-standard distribution is equivalent to finding the probability that z, a standard normal distribution, is less than, what would this result in? 13 minus 10 is 3 divided by 2, so that's 1.5, right? So I'm looking for this probability. Now this one, again, using the same trick, I can find it from my standard normal distribution table, right? This is already a standard normal distribution. So go to that table, right? And placeholder, get me the image. Let's put it up here so it doesn't interfere with, let's give it enough space to be large enough, right? And then bring it on. Hello. And we are looking for z less than 1.5, so this guy, right? 1.5. So this is equal to 0.9331193, right, from the table. Now I got this value. I should do what? I should take it, right, and substitute it in this formula, right, the one that allows me, right, because this is exactly the same as this. So basically the probability that x is greater than 13 is equal to 1 minus, what was the value? 0.933193, and then I've solved the problem, right? So simply you do the mapping. The mapping is always going to give you on the left side a standard normal distribution and the corresponding small z value that you need to use to get the probability from the table. Once you get this probability, is the same as this. So this probability for standard normal distribution is the same for this non-standard one. You substitute it directly in your formula and you can get the probability that you are looking for, right? So great. So this slide is exactly saying what I just said, that in order to solve for a probability of a non-standard normal distribution, all what you need to do is map it to a standard by subtracting the mean, dividing by the standard deviation. This side is going to be your standard normal distribution, just symbolic. The other part where you use the actual values of the mean, the variance, or the standard deviation, and the x value that you are looking for is going to correspond to a particular z, small z value that you will use to get the probability from the table. And this probability is the same as this one. The probabilities are the same, right? Nice. Okay, so let's see one more example where we use this operation, but in the reverse. So first of all, in a more complicated problem, and then we'll use it also for the reverse problem. So here, simple example, asks you to find the probability for the current, the problem that we have just been looking for, greater than 9, less than 11 milliampere. Now again, this corresponds to Z, right, which is this guy, capital Z, standard normal distribution, greater than this value minus the mean divided by the standard deviation, which is going to give you minus 0.5, less than this value minus the mean divided by the standard, which is going to give you 0.5, and then the probability that you are in this range can be mapped into being smaller than 0.5 and minus the probability of being smaller than minus 0.5. We've seen this mapping before. Get both from the table, right? Okay, and then substitute them. Voila, you got the probability that you are looking for the non-standard. You map the problem to standard, you found it from the table, and that gives you the value. Now let's look at solving the inverse problem. Determine the value for which, the value of the current, for which the probability that the current measurement is below this value is going to be equal to 0.98. So what he's asking for here is find small x such that the probability of your normal distribution, capital X, smaller than this small x is equal to 0.98. Now again, right, this is a non-standard because x has a mean equal to 10 and a variance equal to 4, right? So we map the problem. This x that we are looking for, okay, is here. Then this probability that we are looking for is the probability that the capital X minus mu divided by the standard deviation is less than the small unknown x minus mu divided by the standard deviation. Left side is going to be simply z, smaller than some function of the small x that we don't know. So we still have the small x here, right? X minus 10 over 2. Now consider all of this as if it is just a small z. So that small z is still unknown to me because I don't know the small x. What do I need to do to find the small z? I have the probability that my standard normal distribution is less than this unknown small z, and I need to find the small z from the table. So again, put the table on, right? And once we put the table on, should be able to find the required probability, right? So bring the table to see it here, and let's see, 0.98, 0.98. So 0.99, 0.97, 0.98. I think that's the closest, right? Which corresponds to small z equal to 2.6. So now we know that this will give me a small z from the table equal to 2.2.0 2.06, right? So that's my small z. But what I need to find here is the small x, right? But this small z that I found, right? So the small z, as we mentioned above, is equal from the table is 2.06, as we got it from the table. So this small z corresponds to x minus 10 divided by 2. So this x minus 10 divided by 2 is the small z substituted here. So 2.06, this means that your x is equal to 2.06 times 2 plus 10. And this is going to give you the x that you need to find, which is going to be approximately 14.1. Now, the value that he got from we said there is some approximations when you get values from the table. So the value that he got from the table was 2.05 rather than 2.06. And again, I will deal with those like rounding issues, no problem with that, as long as they are very reasonable, right? Okay. So this shows you how you can also solve for non-standard normal distributions using the tables of the standard normal distributions. Okay. And last but not least is this just figure shows you what the case that we have been solving was for this normal distribution, which is the non-standard one. We mapped everything to the standard one, solved from the tables, and brought it back to the non-standard. Just shows you that we have been doing mapping, so there's nothing really extra in this.